Hey everyone, good day. I'm Denise Cabangunay from Step 12 Leviticus, Kit number 1 of Robotics G.
I am Banaag from Step 12 Leviticus.
I'm Janille R. Ducao, grade 12 Leviticus.
I'm Louise, Yvonne, Guro, grade 12 Leviticus from kit number 1.
In this activity, we learned how to make the Arduino communicate with the serial monitor by printing "Hello Student" repeatedly. At first, some of us were confused because nothing appeared until we realized we needed to open the serial monitor. This activity taught us how sensors send live data to the serial monitor. Our main challenge was connecting the temperature sensor correctly. Sometimes the reading didn't change or showed weird numbers until we fixed the wiring. It felt satisfying once it worked and we could actually see the numbers react to our touch or the room's temperature, just like a digital thermometer. In this task, we tested how the Arduino detects a button pressed. The tricky part was pressing the button and not seeing anything happen at first. Turns out the wiring or orientation of the button was wrong. This activity was really fun because we got to control an LED just by typing on the computer. The hardest part was figuring out why nothing happened after typing. We later realized we needed to press enter or send for the command to work. It felt like turning our laptop into a mini remote control, showing how Arduino can respond to human commands through simple communication. Here, we used a photoresistor to measure how bright or dark the surroundings were. The challenge was testing it under different lights. Sometimes the numbers didn't change much until we covered the sensor completely or used a flashlight. It helped us understand how light sensors are used in automatic lamps or street lights that turn on at night. The HC-SR04 ultrasonic sensor to measure the distance of an object and displayed it on the serial monitor. At first, the sensor couldn't detect the object, but we fixed it by checking and securing the trig and echo pin connections. After that, it measured distance accurately, which can be applied in parking sensors or automatic doors. The ultrasonic sensor measured distance and displayed it on an LCD screen. The LCD didn't show readings at first, but after correcting the I2C address, it worked. This component can be applied in automatic measuring systems and smart robotics. 3. We made an obstacle detector that lights up an LED when an object is near. The LCD didn't work at first, but after checking the connections, we got it working. The system can be used in obstacle avoidance and safety alarms. 4. This activity simulated a parking assistant using LEDs and a buzzer to show distance levels. At first, the buzzer didn't sound and one LED wouldn't light up, but after fixing the wiring, the system worked well for vehicle parking assistants.
For the activity 1, using the IR proximity sensor, we the students will use an infrared sensor to detect the difference between a black surface and a white surface. By observing the sensor's digital output, students will discover how surface color affects infrared reflectivity. For the activity 2, students will build a basic proximity-based alarm system using a digital IR proximity sensor and a buzzer. When the sensor detects a nearby object, like a person or hand, it triggers a buzzer to sound an alarm and light up an LED. Just like activity 1, we did not encounter any difficulties in doing this. For activity 3, students will use an IR proximity sensor module to count how many times an object, such as a hand or person, passes in front of the sensor. Each time an object is detected, the counter increases by 1.
In this activity, we controlled a DC motor using a push button and a MOSFET connected to an Arduino. We had minor issues with wiring the button, but after fixing the connections, the motor worked properly and can be applied in simple motor-controlled devices. We used a potentiometer to control the motor speed through PWM, but at first the MOSFET didn't respond even when the potentiometer was turned. After troubleshooting the circuit, we got it to work, and this setup can be used for projects that require adjustable motor speeds. This activity introduced us to turning a DC motor on and off using an H-bridge. The challenge was figuring out the correct pin connections, and our motor didn't spin at first because of wrong wiring and loose jumper wires. But once we fixed it, it was cool to see it move automatically like a small machine turning on by itself. Here, we controlled how fast or slow the motor spins using PWM. We struggled at first to notice speed changes since the motor seemed too fast, but after adjusting the delay and holding the motor lightly, we could feel it speeding up and slowing down, like a mini fan with adjustable speed. This time, we made the motor spin in two directions, which is forward and backwards. It was a bit confusing at first because the motor didn't change direction until we checked the jumper placements. Seeing it reverse was really satisfying, and it made us understand how robots or cars can move backward and forward. 4. In this activity, we used two buttons to manually control the motor's direction. The challenge was getting both buttons to respond properly. Sometimes the motor wouldn't move because the buttons weren't pressed firmly or were in the wrong pins. Once it worked, it felt like controlling a small robot car using switches. This activity combined both direction and speed control using buttons and a potentiometer. It was tricky to wire since there were more components and some of us mixed up the pot spins, causing unstable speed. But once we saw the motor change speed smoothly and reverse its direction, it felt like creating a real motor controller that is similar to how cars or machines adjust speed and direction.